Hi, this is Yiming. In this video, I will present our solution to autonomous 3D exploration. This work is co-authored with Alessio De Bue. In this work, we follow the next best view paradigm to explore an unknown environment with a depth sensor. At each time step, the system captures a new depth measurement and reconstructs partial of the scene. The system then chooses among the next candidate movements the best one that maximally explores the unseen area. We formulate the next best view estimation as a classification problem and propose an efficient representation for the 3D reconstruction status. This representation can be combined jointly with the depth image to train a lightweight CNN for MBV estimation. So how do we represent the 3D reconstruction history? The answer is using a utility map through ray tracing. Given a camera in a reconstructed space, we trace a set of rays within a defined field of view, starting from the camera pose towards the 3D space. Each ray corresponds to a utility value. The utility should encourage the next best view towards unexplored area. We set the utility value to 1 if the ray does not encounter any visited voxels. Otherwise, it will be set to 0. The field of view of ray tracing defines the extension of the reconstructed area to be considered for deciding the next best view. We experimentally prove that seeing the reconstruction neighborhood with a 2-step range is a cost-effective option. We now introduce our proposed ExHistCNN. ExHistCNN is essentially a classifier for the MBV direction. The network architecture is a lightweight CNN with 3 convolutional, max pooling, and fully connected layers. The network output is one of the 4 candidate directions: up, down, left, and right. The input data contains both the current depth observation and the reconstruction history in the format of a utility map. One important question to answer is that how we can best combine the 2 inputs to facilitate the network learning. To this end, we explored several data combination formats. One intuitive option is just stacking them as 2-channel data. We name this model as CNN 2D. As the depth image is captured at a smaller field of view compared to the utility map, with the intuitive to reserve the spatial correspondence between the 2 inputs, we first rescale the depth image with 0 padding, and then stack them into a 2-channel input. We name this model as CNN 2D scaled. Moreover, to facilitate the directional learning, we partition the utility map corresponding to each direction, and then stack the 4 partitioned utility maps with the depth image to form a 5-channel data. We name this model CNN 5D. Finally, to justify if the combination is actually beneficial, we also train models with either depth or the utility map or its partitioned version. We used 33 synthetic rooms from SunCG to generate our dataset. For each room, we render 642 viewpoints distributed on a sphere surface looking out at the environment. To make the dataset generation tractable, for each viewpoint, we discretize its neighborhood reconstruction history into 6 status, from 0% to 100%, with 20% as a gap. Each status is approximated by reconstructing the scene using the depth frames corresponding to the viewpoints that are sampled based on each reconstruction status. Now we introduce how we perform methods evaluation for 3D exploration in this work. We tested the methods with both synthetic rooms from SunCG and real room scans from Matterport 3D. All candidate camera viewpoints are distributed on a sphere surface as introduced previously. The exploration performance is measured by the surface coverage ratio. We compute it as the ratio of the number of surface voxels reconstructed using autonomous methods over the number of surface voxels of a complete reconstructed room. We compare different variants of our ExHistCNN to baselines and the state-of-the-art methods. Oracle DEPS2 serves as a reference for the best reachable result for the learning-based strategies. It integrates the depth frames of next two steps that corresponds to each candidate direction into the current reconstructed scene for selecting the next best view. Also, in order to justify the choice of the lightweight CNN, we compared with promising models that use features extracted from the pre-trained ResNet to train a multi-layered perception classifiers. The input data for training MLP-based models follow the same format as ExHistCNN-based models. Finally, we compared against a set of baselines. Random strategy, random selects the MBV. Base gain selects the MBV based on the sum of the partition utility maps. Count selects the MBV by counting unknown voxels for each candidate pose. And finally, comp gain selects the MBV using both the output from the CNN depths for direction selection and the entropy-based utility for each candidate pose. We first show the exploration performance evaluated on the synthetic rooms. On the left, we plot the coverage ratio achieved by different methods over time, while the right one shows the mean and standard deviation of the coverage ratio achieved at saturation. All autonomous methods terminate at 150 steps, while most methods saturate in their exploration performance. Oracle DEPS2 functions as the performance upper bound for all the learning-based methods. We can see that our ExHistCNN variants, CNN2D and CNN5D, leverage the depth information to explore faster compared to CNN4D at the earlier stage, and saturate at a similar coverage ratio which approaches to the performance of Oracle DEPS2. In the early phase, we also notice that CNN2D explores faster than CNN5D and has a similar exploration speed as Oracle DEPS2. When testing on real room scans, we can see that our variant CNN2D and CNN5D are still the quickest in the early phase compared to other methods. However, at saturation, they are surpassed by other methods with handcrafted MBV metric. This suggests that our learning-based strategy may require further domain adaptation when transferring from purely synthetically trained models to real-world scenarios. In this work, we demonstrated the potential of our proposed ExHistCNN for encoding depth observation and 3D reconstruction setters for the autonomous exploration task. ExHistCNN-based MBV methods are computationally efficient and able to explore the space faster in the early phase when evaluated with both synthetic and real rooms. While CNN2D and CNN5D are approaching the Oracle MBV performance with a synthetic dataset, we also observe a clear performance drop at saturation when evaluated in real room scans. This indicates the need to bridge the domain gap between synthetic and real-world rooms, which will be further investigated in our next work. Our code and dataset is available online. We look forward to see you on the live session in ECCV for more details. Thanks for listening.